A nice way to visualize a function from R2 to R is to think of it as a surface, like this. You see the xy plane there, and the function is given by the surface floating above it. Now if you take a point on the xy plane, then there is a corresponding point on the surface. The height of that point above the xy plane is the value of the function at that particular point. Now, when we think about differentiating such a function, we have to visualize the tangent plane to the surface at that point. It is a plane like this. The plane is a plane that passes through that point on the surface. But that is not its only property. You might have lots of different planes all passing through that point on the surface. But the tangent plane is a special plane among them. To understand that, take any other point on the xy plane. Then, corresponding to that point, there will be 2 points, one on the tangent plane and one on the surface. There is no guarantee that these 2 points will coincide. For example, here we can see that there is a vertical gap between them. Now, the difference between these 2 vertical points, the vertical difference between these 2 points, they will always be situated one above the other. So this vertical distance will of course go to 0 as the point on the xy plane will move towards that point. However, there is something stronger which is true. If you divide that vertical height by the distance of the 2 points in the xy plane, then that ratio will also go to 0 as this point moves towards that point. In other words, that vertical gap will be of the order little o of h, where h is the distance in the xy plane between these 2 points. Now one may show, though we are not going to show that in this class, that such a plane, if one exists, must be unique. And this plane is called the tangent plane. Now any plane has the equation of the type z equal to a plus bx plus cy. If you take this plane to pass through a particular point, in that case the equation will be like this, where the plane must pass through the point x0, y0, z0. So you see, such a plane is given by 2 slopes, the coefficient of x minus x0 and the coefficient of y minus y0. It turns out that these 2 slopes are precisely the partial derivatives of f at that point x0, y0. The coefficient of x minus x0 is the partial derivative of f with respect to x evaluated at that point x0, y0. Similarly, the coefficient of y minus y0 is the partial derivative of f with respect to the second variable evaluated at x0, y0. In particular, if the tangent plane exists, if such a plane exists, then f must have these 2 partial derivatives well defined. We will never have any problem there. However, the converse is not true. It is quite possible for a certain f, the 2 partial derivatives may be well defined. So, you can still write down the equation of the plane, but that plane need not be the tangent plane. Sometimes beginners are thrown off by this fact. How come the tangent plane exists, yet function is not differentiable. In fact, this particular formula may not be the tangent plane if f does not satisfy certain other conditions. If those conditions are satisfied, then this will be the tangent plane. So the mere existence of the two partial derivatives is not enough to guarantee differentiability of f. I am not giving you any other condition on differentiability of f. I am merely saying if such a plane exists with that property, that the vertical gap will be of the order of little o of h. Now, if we make some further assumptions which are analogous to assuming existence of second order derivatives of the function, I am not going to go into the details, then you can make an even stronger statement. That vertical gap will be of the order big O of h square, which means if you take the length of the vertical distance and divide it not by just h but h to the power say 1.1 or 1.5, some power which is larger than 1 but smaller than 2, then also it will go to 0. So that is a stronger condition. You can go on like that up to 1.99999. What happens if you take h square in the denominator? I cannot guarantee that the limit will still go to 0, but I can guarantee that the limit will exist finitely. So you need some extra condition other than existence of the derivative of f at that point. You need something analogous to existence of second derivative. And that actually is what is called the first order Taylor approximation to this bivariate function f. You write it as the function is this plane plus some error which is of the order of big O of h square.